Hello again. Tonight we're going to talk about making the invisible visible. Yeah, I know it's a clickbait title. We'll get to the details. So the electromagnetic spectrum is that thing in which radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma all exist at different wavelengths and frequencies. And there's a slice in the spectrum that the human eye, human vision can perceive. That's just called visible. Longer wavelengths are the ones on the left, and the shorter ones are the ones on the right. The ones on the left are also lower energy per photon. The ones on the right are higher energy per photon. And the goal, and what I've researched this week from a news article from last week, is it looks like there's a way that you can take invisible photons from the infrared band and go through a kind of a filter that will change them from infrared to green, which makes them visible. This is not referring to like having an infrared camera that you then go in and change the colors to make it, false colored visible, and you put that on a computer screen. This is a direct transfer. And I'm not talking about doing blackout masks where you take like a red filter that will only let the red light through and everything else goes black. So in radio, if you have a radio tuner and you want to listen to a lower frequency than that tuner will tune, you add a device on the front end before it gets to your tuner called an up converter. And the up converter will convert the longer wavelength, shorter frequency radio waves into shorter wavelength, higher frequency radio waves. This is called up converting. So if you want to listen to 10 megahertz, you'll plop on your up converter and you'll listen to 10 megahertz at like 120 megahertz. It'll up convert. And if you've ever seen a satellite dish, like a DirecTV satellite dish, there's that blob that sits out on the end of the antenna, right where the focus is, the little round thing, and then there's like a tube or a box behind it. Inside there is something that takes the very short wavelength, high frequency radio and down converts it to something that's easier to carry across wire and then easier to get your TV to tune. So they down convert. So up converting and down converting are commonplace in radio. Now, when you up convert something and you take a slice out of that wider wavelength and you put it into a narrower wavelength band, it's pretty easy to do because that wide bandwidth occupies less frequency range when you move it up. So if I want to listen to 0 to 100 megahertz, I can take that and fit it into the 100 to 200 megahertz of my like 2 gigahertz bandwidth radio receiver. So it's real simple to just like grab a wide chunk from the low end and plop it into what would occupy a very narrow chunk at the higher end. Not so if you're going the other way around. If you want to convert a high frequency band to be able to be received by your low frequency, narrower bandwidth radio, you got to take a smaller slice because that wider bandwidth, higher frequency is going to occupy a lot of the received bandwidth of your radio. So for example, if I wanted to receive NASA satellites, which are up in the 6 to 8 gigahertz range, I can't just go, well, I'll take 4 to 8, and then I'll drop that on a down convert into my maximum 2 gigahertz radio. It won't fit. I'll only get 50% of it. But if I constrain myself and I say, well, instead of 4 to 8, I'll listen 6 to 8, 2 gigahertz. Now that will exactly fit, but it covers my entire radio's bandwidth. Up converting, easy. Down converting takes a lot more space. And when you tune a radio, all the radios, at least as of, I guess, the late 1950s, are superheterodyne radios, and they all receive at one particular frequency for one particular bandwidth. And then if you want to tune to like shortwave 1 or shortwave 2 or whatever, it has chokes that will tune to whatever band you want, and will take like shortwave 1 and squeeze it into the intermediate frequency band that the radio can actually tune on. So you've already got existing radio technology that does this squeezing of radio bands to fit within a common tuner. Same sort of thing. We're just going to do it with light. Radio, light, it's all photons. So you could either have an analog front end of your optical receiver and do an analog to digital conversion, convert it from an analog signal to digital, and then process it. That's kind of like the false color mapping, how you get something invisible to be visible. That's called indirect. Then there's direct mapping. Many people don't know that the average inexpensive green laser pointer is actually an infrared laser. It's not a green laser. What they do is they take the infrared beam coming out of the laser and they run that through what is known as a frequency doubling crystal. Frequency doubling as in it takes the reduced frequency of the infrared light and it doubles it by taking 2 photons in and spitting typically 1 photon out, or not always 1 photon out, sometimes no photon out, because it's not perfectly efficient. It can lose some of that photon flux due to heating. 2 photons go in and sometimes 1 photon comes out, and now you have it at a different frequency and different wavelength, which might be more visible to the human eye. And this is how an infrared laser pointer becomes a bright green laser pointer. Even though the total number of photons as it transitions from infrared to green is less. So it loses some of those photons during the translation. If you ever held your laser pointer on for a while, you notice it get warm. That's not like the electronics or the battery getting warm. That's the actual crystal that's doing the frequency doubling, getting warm through inefficiencies. And so not all the photons that come out as infrared come out as green, but green is so much more receptive to the human eye, and it looks really bright, even though it's not. Some folks are working in this area, and I couldn't help but notice it. And yes, good. Keep it up. And what they're doing is they're using this approach of taking infrared in, running it through a special kind of filter, and producing visible light out. But they're not just doing that, because if they did that, then a lot of the infrared would come in at different wavelengths, and so it would look foggy. And we'll get into how that affects hydrogen alpha astronomy telescope solar observing towards the end of the presentation. But just know that we're used to looking at specific frequencies of light with our eyes, and if too many of them are coming in all at once from different sources, that's different polarizations, and it looks too bright for us. This is why we get polarizing sunglasses, to get just the stuff that's coming at us and not all the scatter. Well, they're not only using the frequency doubling crystal, they're creating little tiny ridges at the billionths of a meter scale, at the nanoscale, onto the surface of this crystal. These are referred to as metamaterials because they're being manipulated physically, scarring and ridging and channeling at billionths of a meter. And what that does is that reduces the scattering so that the light coming through is all in the same direction. And by doing that, they can make things sharper. You get less of the infrared fog being carried over into the visible spectrum. So this image of the 2 kangaroos, you can see the red kangaroo coming in and the green kangaroo coming out. I actually doctored their image. I'll admit to that, because their image was not quite accurate. If you have a red infrared image of a kangaroo coming in and you convert it to ranges of green, their kangaroo was showing browns and whites and tans. Like, you wouldn't get that. You would get different brightnesses, different color variations of green, just like you get different color variations of red when you're looking at the infrared. So I greened up their brown kangaroo. So you can see the red image here of the 9.0 and then the lines. Now that's actually captured with an infrared imager. So it's only seeing an infrared. But if you go over to the right, you can see the same source that has been converted from infrared, which would be invisible, to green, which is visible. And see how there's inversion? The red comes out dark, and the things that are not red come out bright. So that's part of the ridging, is to make things like fine lines of light versus dark have only the light coming in one direction. That's why it's still a little fuzzy. You can see it's fuzzy on the top and the bottom of the curve of the 9 because they're not vertical this way, they're horizontal this way. That's why they want to test vertical lines and horizontal lines. And you can see the vertical lines are skinnier and there's more brightness between them than the horizontal lines, which are fatter and there's less light between them. And you can see that because of the diagonal in the 0, there's almost no light coming through because the space is too small. So they've got things they need to work on. But they're trying other things like the sun spoke down at the bottom, and then they run that through, and you can see like an individual, they put dotted lines around it, but an individual spoke, and they're focusing on not just horizontal and vertical, but what about if it's at a diagonal? What about if it starts out wide and gets narrower? So they're paying attention to all the optical minutiae. But once they get this working, you'll be able to have a metamaterial filter that will take a band of infrared and upconvert it to a range of greens. And now you can see the invisible infrared in a range of greens. So if you've heard of sunglasses, there's no batteries, no electronics. It's just a crystal that's been fabricated at the nanoscale. And now you have night glasses. You can see what would be invisible infrared in shades of green. For those that are suffering from cataracts, this will be a godsend because you can now still drive at night. Here's the thought. If they can take infrared and make it green, and it's at specific wavelengths like 1550 nanometers up to 622, they're up converting to that level. If they shift it just a little bit from 1550 up to 656, 656 is hydrogen alpha. Hydrogen alpha is what all those amateur telescope owners want to look at the sun, because the prominences, the plasmas coming off the sun, produce a lot of the alpha band hydrogen emissions. So they like to look at them at 656 nanometers or thereabouts. If you had something that could take that very, very dark red and make it brighter green as a filter, you could add that to the back end of your hydrogen alpha telescope, and now you wouldn't have to put like a blackout cloth over your head in the telescope in order to see the real dim, deep red features of the solar prominences and flares. You could actually just put a filter on there and see it in green. Even if you lost a lot of the photons and the inefficiencies of the crystal conversion, there would still be enough brighter green light coming out that you would see it as bright. Easier for human vision, easier for photography, no electronics, no power. That would be something they could do if they were interested in doing that. Maybe some future generation of HA telescopes will connect the dots. So while we're talking about hydrogen alpha telescopes are centered around 656 nanometers, but like only about 8 nanometers, a fraction, I put there about 10 nanometers, but really the bandwidth that they're observing is only about 8 nanometers wide. And why would that be the case? Because on the edge of the sun, you're looking over the limb of the sun at the prominences coming off the sun. If those prominences are coming towards you, they're very high velocity. The color, the wavelength is going to be shifted towards blue. Now, it's not going to be blue. It's just going to be not as red as you would expect. If the sun has the prominences going away from you, they're going to be red shifted. They're not going to be like redder than red. They're just going to be a little redder than that 656 nanometers central line for hydrogen alpha. So if you include in what you're looking at all of the red stuff coming at you that's slightly blue and all of the red stuff going away from you that's slightly deeper red, when all you want to see is the stuff going sideways and not shifting, then you need to filter out all that other stuff. because if you didn't narrow it and filter it all out, your hydrogen alpha telescope would just be looking at a fog, because you'd be seeing all the red coming at you in different shades, all the red going away from you in different shades, and then all the red that you really wanted to see coming out. It would just look like a red fog. And how do I know this? Because I've actually built a hydrogen alpha telescope front end that filtered out all of the ultraviolet, the visible, and the lesser infrared, and narrowed it down to that 656 nanometer band. But it was about 20 nanometers bandwidth. And I could put as many gray levels as I wanted on that thing to knock down the brightness. But the end result was, all I got to see was a red fog. That's because the thing on the back end of the hydrogen alpha telescope, called an etalon, narrows that red fog so that you're only looking at the particular wavelength of hydrogen alpha that's, the stuff coming off the edge of the sun going away from the sun. You're only looking at that. You're not looking at the stuff coming at you. You're not looking at stuff going away from you. Just that flare at the edge, which allows you to see nice, sharp prominences. No fog. Well, when your hydrogen alpha telescope heats up as you're staring at the sun for a while, why is it you have to keep tweaking the etalon, keep adjusting it? It's because that much heat will make things expand in your telescope. And the thing that it makes expand is the glass plates in your etalon. And therefore your 8 nanometer separation gets a little wider or narrower depending upon the tilt angle of the two plates. So you have to give it a little tweak every so often as the plates heat up, because if you don't, instead of you looking at the stuff that's coming out the side, you might be looking at the stuff that's coming towards you. And that wouldn't look as sharp because it would be bent down because it's curving away from the sun towards you. So it wouldn't be as sharp and as pretty to look at. So you need the etalon, and you need to keep tuning it to get just the stuff pointing up. I know, minutia about an HA telescope. So in conclusion, there are wavelengths of the electromagnetic spectrum that are invisible to humans. One area of that is infrared. Radio is invisible, but we have the up and down band shifting stuff that allows us to tune things that we couldn't tune without them. We can do this either analog, using crystals, or digital, by capturing the image and then recoloring it and showing it on a computer display. But we can do this with laser pointers, change them from infrared into visible. Why don't we look at doing the same sort of thing for looking at other things, so that whatever light comes in that's infrared gets transferred to a more easily visible green. You could essentially have, if you own prescription glasses like I do, and you don't want to have to go spend a lot of money to buy prescription sunglasses, you get those inexpensive clip-ons that will polarize the light and make your regular sunglasses, make your regular glasses into sunglasses. This would be something similar. If you created a filter that would convert infrared into green, you would have night glasses. So you could slip on a pair of clip-ons that were night glasses and drive more safely in total darkness. Headlights would not need to be 3,000 watts, because everything out there at night, given that the air is cooler, puts out heat, and you can see that in infrared. Night glasses. And also, if they did this for eyepiece filters, you could have an HA telescope that wouldn't be hard to see in dark red. It would be much easier to see in shades of green. And 2 pages of links, all kinds of stuff. My favorite material, lithium niobate, LiNBO3. It's the key of nonlinear optics. How do you make light behave at the quantum level? And then a whole bunch of research articles on frequency doubling. And then, of course, I have to post the laser safety document from Harvard. When everybody says, I bought myself a 12 megawatt laser. I tried to point it at my face and it burned my nose off. Like, okay, read this document. Don't do that. I very much am trained and aware of laser issues, and I use them safely. I have a 5-watt laser in my CNC router sitting behind me, and I have an entire enclosure that I built that has plexiglass panels that are laser safety coated for that specific wavelength. I see the beam, even though the panels are green, I see the beam as kind of a very whitish blue, because it does a frequency shift of the laser from ultraviolet down into a bluer visible, and then the green stops most of the brightness from coming through, so I can safely watch it. But in addition to that, I also have laser safety goggles that go on over my eyeglasses. Risk assessment, yes, I do that all the time. So, comments, questions? Anybody want a pair of night glass clip-ons?
Yes.
Yeah.
I think I would rather get the genes from a mantis shrimp and just have them put in, and then I can see infrared, ultraviolet, and polarization.
Well, you'd need the gene because you would need extra receptors in your retina.
Right.
It's not just the existing receptors can see a broader range. Mantis shrimp we have 3 color cones. They have 5. So, yeah, it's that tiny little mantis shrimp that, physiologically speaking, their retinas are far more complex than ours are, and they can see much better. If you're going to put one in your aquarium, make sure it's a thick-walled plastic aquarium, because if it's a thin-walled glass aquarium, mantis shrimp have been known to use their little flip maneuver, and their claw travels at supersonic speeds underwater, because it's a matter of angle and muscle. And the angle is so shallow that you just need to give it a little flip, and the arc that it traverses accelerates underwater through, what do they call it when the bubbles move over the outside?
Cavitation.
Yes, yes. Their claw cavitates through the water and allows it to move at near supersonic speeds. So when that claw hits their dinner's shell, it'll just explode their dinner's shell, and now they can eat whatever it is. But if it happens to see its reflection in your glass tank, your glass-walled tank, and it wants to make a maneuver, an aggressive maneuver towards itself, and it fires its claw, it'll shatter the glass on your tank. So, mantis shrimp, you want a thick-walled or a polycarbonate glass tank, not glass. Yes, I'm an ichthyologist too. Anything else anybody wants to say about tonight's presentation before I stop recording? Hearing nothing.